morning, afternoon, or evening. Welcome back to Mr. Morrow's afternoon. How y'all doing today? All right, guys, I like that. That was a good intro. Guys, today we're going to continue with trigonometry, but I added a new lesson, and this is going to be our part 3. You have another part 3 you got to watch that is valid. Guys, today we're going to hopefully get rid of a lot of the confusion in trig. Now, I have a lot to give you, okay? So please bear with me. There's going to be a lot of information thrown at you, but I'm hoping that it's all going to make sense today. And the other good thing is that a lot of these slides we've already seen before, okay? So first off, this first slide, very simple. We have seen this before, but let me make sure I explain it perfectly. Whenever we have a right triangle, guys, okay, and we're working with trig, we're going to be working particularly from one angle, okay? That's going to be, usually it's called my reference angle. That's where I'm coming from. That's the angle that I'm using to calculate different trig functions. So from this particular angle A, this particular angle theta, from there, this is the opposite. Okay, it's across from the theta. The one immediately next to the theta is my adjacent. And then the one that is across from the 90 is my hypotenuse. Now, a lot of people will say, Moro, but the hypotenuse is always next to. So isn't the hypotenuse, isn't that also adjacent? No, never. The hypotenuse is the hypotenuse is the hypotenuse. The hypotenuse is only the hypotenuse and will only be the hypotenuse only forever. And it is known that it's the hypotenuse because it's across the 90. Guys, like I know that sounded crazy, but for real, the hypotenuse is the hypotenuse and that's it. It's never the opposite. It's never the adjacent, no matter what. Okay, my brothers? So that's pretty simple. Boom. Alpha and theta. Guys, this is called theta. And this guy here, as you can see, is called alpha. These are just Greek letters that usually are used in trig to represent angles. Okay? So now you know what theta is and what alpha is. Those are just symbols that represent angles. Now, when we're talking about angles in general, guys, I got to tell you, I'm going to show you how an angle works, okay? And an angle works as follows. You have an initial side, which is here in red, okay? And the angle starts at, hence the initial side, that's initial, and it starts traveling. And eventually it stops. When it stops, guys, that's the termination of the angle. So where it stops is called the terminal side. So that's why the red here is my initial side. That's where I start. Okay. Terminal side is where I end. Should have done that in blue. Terminal side is where I end. And the angle actually travels from initial side to terminal side. That's how an angle works. When an angle is going counterclockwise, it's positive. Now, when an angle goes clockwise, when it's going down clockwise, you have a negative angle. So this negative angle worked the same way. The only thing that happened here was as follows. It was here at the initial side, but this time it went down. So when it goes down, when it goes clockwise, brothers, that's going to be a negative angle. When it goes counterclockwise, it's going to be a positive angle. And that's the way angles are formed. Okay? Angles can go round and round as well. Let's say this angle didn't want to stop there. Let's say it just wanted to keep going. Guys, this is similar to what's happening in your engines. And as the crankshaft turns, it's making the pistons go up and down. And it can go faster or slower. But where it ends is the terminal side. You with me there, guys? Okay, that's how an angle is formed. Questions, comments, concerns? Next, let's draw some angles then. I want to draw the angle 225 in green. All right, well, The angle 225 in green, very simple. It's positive, so we're going to have to go counterclockwise. And I got to go 225 degrees. Well, guess what, guys? It's my initial side. I'm going 90 plus 180 plus how much more to get to 225? Plus 45. Go ahead and label the 45 here because that lets the reader know, hey, I went 90 plus 90 is 180 plus 45. So my theta here, my angle is 225. It's kind of cool, isn't it? What's my terminal side? This guy right here. That's where I ended. That's my terminal side. Does that make sense? Promise? Talk to me? What would be the angle? The bottom part? No, very good question. The question here was, what's the angle? Okay. The angle is this guy right here. This whole top part. Now, you don't work with that though. Remember that I said you form little triangles? And this is coming later in the lesson. You work with this guy though. This guy right here, the 45. That is what's called your reference angle. And that's what we're going to work with always. But we're not there yet. But you asked, that's what we work with. But the real angle is what we just drew here in green. Cool? Okay. Now, 495. Okay, well, 495, I know I can go one full circle, that's 360. 360 plus 90 is 450. 450 plus 45 is 495. So this angle here, guys, went 360 plus 90 plus 45. You can label the 45 here to show the reader that, hey, I went one full circle plus then another 90 plus then another 45. And that whole entire angle there is 495. That's my theta. But what's my reference angle? My reference angle will be this guy right here. We'll call it alpha. That's who I'm going to work with. I will show you how to get reference angles in a little bit. But I just want to just kind of give you a preview. And now, how do we do negative 210? Well, negative 210, starting at my initial side, and I'm going down now. So I'm going down 90, 180, and then another 30. And that right there is my angle theta, which in this case is negative 210 because I went clockwise. I know I'm throwing a lot and it's just the beginning, but I want to make sure you're with me so far. Everyone understands so far what our initial side is, what the terminal side is, how to draw an angle, how to recognize the opposite and the adjacent and the hypotenuse from a given theta. Everything is yes there, what I just said? Promise? Thank you, boys. All right, so now, let's continue. Now, real quick, do you remember the 495, guys? How I wrapped around one whole time? Okay, keep that in mind. We're going to talk about coterminal angles. Think about the name, guys, coterminal. Coterminal means that they end at the same exact spot. Coterminal angles mean that they end at the same exact spot. So if they end at the same exact spot, that means they're going to have the same exact reference angle. If they have the same exact reference angle, that means they're going to have the same exact trigonometric functions. How do you find coterminal angles? By adding or subtracting multiples of 360. The only way to show you this is by showing it to you. I go ahead, I already set this up for us, and my initial side is in red, and my blue is going to be my terminal side. So I go, okay, how about I go right here? And this theta here, let's say, I went 90, 180, and let's say that I went another 60. So my theta here is 180 plus 60, so this is 240. I just drew an angle of 240, correct? Okay, now, I want a coterminal angle. Guys, what's 240 plus 360? 600. Okay, let's see. Since I added 360, guys, I just found a coterminal angle, and now I'm going to prove it to you in green. 360 plus 90 is 450 plus 90 is 540 plus 60 is 600. So it's the same exact spot that we end in. Check it out. Doesn't it have the same exact reference angle of 60? Ah, so they're going to have the same exact values. Coterminals, like I said, you can find coterminals all day long. All you got to do is add or subtract multiples of 360. Give me 1 second. Let's say I have that 240, but this time I subtract 360. That's going to be negative 120. I'm going to prove to you that this is also a coterminal. Let's go ahead and go down 90 and then another 30. 90 and another 30. Isn't that still my terminal side? Don't I still have the same reference angle of 60? So coterminals are just different ways to write angles, but they're all going to end at the same spot. You had a question, my brother. I knew you were going to ask me negative. That's why I ignored you for a second, because you guys got to let me finish before you ask questions, because if not, you jam me up. But thank you so much, my brother. Does that make sense, guys? That's what a coterminal is. Coterminals you find by adding or subtracting multiples of 360. Moto, does that mean that if you have an angle that's 100 and you add 3,600 degrees, that's a coterminal? Absolutely. Isn't 3,600 a multiple of 360? Absolutely. You would just have to do the circle 10 times, but it would still end at the same exact spot. Yes, sir.
Why would someone put a higher number than 360?
It's not why would someone. That's applications in real life. Remember that motor that I was talking to you about? It's going to spin hundreds and thousands of times, right? Before it ends at that stoplight, and then it calibrates back down to 0, correct? Well, at that point, your angle could have been in the thousands because it kept going and 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 going. It's not until when it stops that you have your actual theta and then your reference angle, and then you can get your value. But as it's still spinning, you're tacking up 360, then another 360, then another 360, then another 360, because you keep going round and round and round. So there's going to be large angles in real applications in life, absolutely. Okay? Now, find one angle with a positive measure and one angle with a negative measure, coterminal with each of the angles. Yes, sir? Okay, because you added. Very good. Very good. So we have here, I added 360. So I found that that's going to be 640. That's one coterminal. Let's go ahead and subtract 360. My negative coterminal is negative 80. Are those the only coterminals I have? No, guys, there's an infinite number of coterminals. Infinite number. How about for B? Give me one positive and one negative. No, not for negative. If I subtract 360, that gives me 220, so that's still a positive coterminal. But now if I subtract 360 again, then it'll be a negative 140 as well. Yes. Because remember, you can subtract multiples of 360. So you know that 540 is larger than 360, so you can subtract negative 720, right? If you subtract 720, then it's going to be negative 140. Yes, sir. Another one would have been 940 as well. But this is a positive coterminal as well. But if I take 580 and I add 360, well, guess what, guys? That's still another positive coterminal. Absolutely. Give me a positive coterminal and a negative coterminal for C, please. Yeah, add 360, so that'd be 480. Subtract 360, that'd be negative 240. Great. Give me one positive and one negative coterminal for negative 470, please. Very good. You're first going to have to add 720. So that's going to be 250. And then now if I add 360 to the negative 470, a negative 110. So coterminals are simply found by adding or subtracting multiples of 360. Very simple stuff. And again, I need you guys to understand one major thing. Negative 470, 250, and negative 110. They all have the same terminal side. That means they all have the same reference angle. That means they all have the same value. You with me here? Promise? Okay. Now, this is from yesterday. This is what started causing a little bit of problems, and I get why, guys. So I'm hoping that I can, once and for all, eliminate any mysteries. Okay, this part right here, you know that the hypotenuse, the opposite, the adjacent, you know that they're labeled from the theta. I'm not going to get into that. But then when we came over here, I said, guys, sometimes you're going to have this point that's traveling, and it's going to be in a circle. Okay? Sometimes it's in a unit circle, sometimes it's not in a unit circle. But whenever it's in a circle, guys, you can find sides of that triangle by using the Pythagorean theorem. Basically, the radius squared equals the side squared plus the side squared. Whenever we're creating trig values, you have to think of this. That hypotenuse is the radius of the circle, guys. That's the radius. And the radius is what controls the circle. The radius is what controls the terminal side. The radius is what controls the trig function values. It's all about the radius. Now, in a unit circle, the radius must be 1. So in a unit circle, 1 equals the side squared plus the other side squared. Yes and yes. Oh, sorry, they had a question. In a unit circle. In this unit circle, from this unit circle, I told you guys that I can get all these values. I'm not going to bore you. We've gone over SOHCAHTOA before. We've gone over the reciprocals. I'm not going to bore you. But I've told you that this came from the unit circle. Then I went ahead and said to you, guys, and in the unit circle, you get these special right triangles. Special right triangles inside of the unit circle. And this is where the confusion started. Because if I'm telling you that a unit circle, okay, is the hypotenuse, and you look at this 45, 45, 90, you're going to say to yourself, Moro, square root of 2 is not 1. That's not in the unit circle. Guess what? You're right. It's not in the unit circle. This came from the unit circle. Do you guys remember the parent functions? Remember how we shifted with the h and the k and the a? Well, think of the unit circle, guys, as the parent function. And as we expand the radius, we are leaving the quote-unquote unit circle, but we are creating similar triangles. And when we have similar triangles, the proportions of the corresponding sides are equal. The ratios of their corresponding sides, rather, are proportional. They are equal. So although this is not in the unit circle, it comes from the unit circle. And let me explain how it comes from the unit circle. Okay? In the unit circle, which I'm gonna show you now in a second, this is not my function. But whenever I have reference angles of 45, okay, I have a special property that affects this triangle. Whenever I have a 45 and a 45, that means that I have an isosceles triangle. The sides are equal. So this side we call S. This side we call S. In this particular case, the S is 1. So what? The hypotenuse of a 45-45 triangle will always be that side S times the square root of 2. So in this particular case, when the sides are 1, the hypotenuse is square root of 2. The 30, 60, 90 triangle works very similarly. It has an exact formula. The side across the 30 is always my small side. We call that S. The side across the 60 is always the small side S times square root of 3. And the hypotenuse of a 30, 60, 90 is always 2 times the small side S. In this particular case, the small side is 1, so therefore the side across the 60 is square root of 3, and the side across the 90 is 2. All of this comes from the unit circle, and all of this gives you this whole table, which is very scary to a lot of people. But I'm going to show you right now how this is not scary at all. Are you ready to rock and roll? Okay. Guys, that's a unit circle. Why is that a unit circle? Well, it's a unit circle because it has a radius of 1. While you are on the unit circle, any point on the unit circle represented as your x, comma, y, while on the unit circle, the x value will be your cosine and your y value will be your sine. Guys, I'm going to go back to the table that we just came from. I'm saying that the cosine of 30, bless you, is square root of 3 over 2, and I'm saying that the sine of 30 is 1/2. Am I not true? Do you see that? That came from this unit circle. However, when you look at that 30, 60, 90, you're like, Moro, that's not the triangle you taught us, though. No, I didn't. Who on earth wants to work with fractions? So what mathematicians did was they said, okay, this is my parent function of all the other trig functions. This is my unit circle. This is where they all come from. What if we go ahead and use scalar multiplication? When we use scalar multiplication in matrices last chapter, don't we distribute that value to all the elements? Well, guys, let's go ahead and scalar multiply this by 2. When I multiply this scalar multiplication by 2, what do I get, guys? My 30, 60, 90 triangle that I just finished teaching you. What's 1 times 2? 2. What's 1/2 times 2? 1. What's 1/2 times square root of 3? Square root of 3. The angles will stay the same, of course. Okay? That's how I got my 30, 60, 90 that we work with. Because I literally just did a scalar multiplication to my unit circle. So, just in case you were wondering, is this inside of a unit circle? No. No. Is this x the cosine? Is this y the sine? No. Is that on the unit circle? No. How do we get the values then of the cosine and sine if it's not on the unit circle? Go ahead and divide by the radius. What's square root of 3 divided by 2, guys? Bam. What's 1 divided by 2, guys? Half. When you have a triangle or a circle that has a radius that's larger than 1, if you want to find the cosine and sine value, literally, just divide it by 2. But again, we're going way further than what we need to. I'm never going to make you expand or contract, but I needed to show you why it is that we use this. I needed to show you that although this is not a unit circle, it came from the unit circle. Does that help at all? Yes, no, maybe kind of sort of, because I don't want to waste your time. Okay, now, same thing with the 45, 45, 90, guys. This is a 45, 45, 90, pure 45, 45, 90 in a unit circle. Okay? But these things are nasty with fractions. So what we did here is to create the 45, 45, 90 triangle that we work with. We went ahead and multiplied everything by a square root of 2. What's 1 times square root of 2? Square root of 2. What's square root of 2 over 2 times square root of 2? Well, square root of 2 times square root of 2 is 4. Square root of 4 is 2. 2 over 2 is 1. And again, square root of 2 times 2 over 2 is 1 again. So that's how we have my 45, 45, 90 triangle. That is 1, 1, square root of 2. No, that's not in the unit circle, but it came from the unit circle. This x and y, no, those are not my cosine and sine. This is my cosine. This is my sine because it's on the unit circle. Points on the unit circle, that x and y, that's my cosine and sine. If I have a larger radius, then the x and y are not my cosine and sine. You feel me? Okay, now, this is a unit circle if I were to go ahead and fill it in. Let me just show you the magic here, guys. Ready? Right here, guys, this is the unit circle of 30. So this is my 1. This is oh my God, what was it here? There it is, my 1/2, sorry. And this is my square root of 3 over 2. Then guess what? This guy here, that's my 60. Then this guy here, that's my 45. Etc., 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 etc. And I screwed those up. The green should have been 45 and the purple should have been 60. If I go here, this is my 90. So every one of these points is just a new location of where the angle ended. You don't have to memorize this. This will be for next year where you have to memorize this. But if you notice, all of these came from here, this table. And this table was made from the unit circle, which was made from the 30, 60, 90, or the 45, 45, 90. That's where all of these values come from. That's how a unit circle works. So again, the unit circle has a radius of 1. Are we always working with circles with radius of 1? No. But whenever we're doing trig functions, they are coming from the unit circle, but it was just a scalar multiplication. We just expanded it. Yes, no, maybe kind of, sort of. Okay. Okay, guys, let's use our skills. Find the exact values of the 6 trigonometric functions of theta containing the point 5, negative 6. Well, 5, negative 6. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. I love it when it does that. Let's try this again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. So let me go ahead and make this guy smaller. Okay. So basically here, guys, this is what happened. I had an angle, and it traveled. Oh, what am I doing? And it traveled. And it stopped right there. So the trajectory of this angle was this way. Bam. Drop this down here. This is my alpha. That's my reference angle. Now, what's my x value here? Well, I'm at 5. So that's 5. So that's 5. And then my y value is negative 6. So that's negative 6. Now, how do I find my hypotenuse? This guy right here. Well, my hypotenuse squared equals 5 squared plus 6 squared. So my hypotenuse squared equals 61. So hypotenuse equals square root of 61. And now, how do I find my 6 trig functions? What's my sine of alpha? Which is negative 6 over square root of 61. I have to rationalize. So it's negative 6 square root of 61 over square root of over 61. What's the cosecant? Cosecant of theta is the reciprocal. So it's square root of 61 over 6. What's the cosine? Negative, yes. What's the cosine of alpha? That's right, which is 5 over square root of 61, which is equal to 5 square root of 61 over 61. What's the secant of alpha? Square root of 61 over 5. What's the tangent of alpha? Negative 6, no, opposite over adjacent. So negative 6 over 5. And what's my cotangent of alpha? So negative 5 over 6. That's power right there, guys. That's power. Yes, sir. That's not a distance, it's a value. It's not a distance. This is a distance from here to here. From here to here, that's a distance. And yes, this is a negative because I went down, but the real distance there is an absolute value of 6. But that's not what we're talking about. We're talking about values. Not bad, right? Okay. Now, find the values of the 6 trigonometric functions for an angle in standard position that measures 300 degrees. Okay. This is where the real magic occurs. Guys, you have an angle of 300 degrees. So that means you have this angle here, and it goes 90, 180, 270, another 30. So this is my theta of 300 degrees, right? But we don't work with theta, do we? We work with the reference angles. Thank you. So what's this value here of this angle here? It's got to be 60 because each corner is 90. So now that's my reference angle. Well, guess what, guys? This is where the 30, 60, 90 triangle comes out so clutch. Look. Look, 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 look. 30, 60, 90. We know that no matter how large this is, I don't care. I'm still using the ratios of my 30, 60, 90. No matter what, because it's a ratio. It's a ratio. So the ratios are going to be the same always. It's just like if I tell you 5/10, isn't that the same as 1/2? Yeah, they're equal ratios. They're proportional. Doesn't matter how I write it. So who's across the 60? Square root of 3, right? Who's across the 30? 30's here, 1. And who's the hypotenuse? 2. So now, guys, what is the sine of 300 degrees? Opposite over hypotenuse, so square root of 3 over 2. But guess what? That's a negative. Yes? You can't use 30 as your reference angle. You cannot. And I'm going to get into this, but the reference angle is always created in between the x-axis and the terminal side. Never with the y-axis, ever. Okay? So this would have been negative square root of 3 over 2. What's the cosecant of 300? You use the reference angle, this guy. Cosecant is hypotenuse over opposite. So this is going to be 2 over square root of 3, but negative. So it's going to be negative 2 square root of 3 over 3. What is the cosine of 300? Adjacent over hypotenuse, so it's going to be 1/2. What's the secant of 300? Hypotenuse over adjacent, so it's going to be 2. What's the tangent of 300? Opposite over adjacent, so it's negative square root of 3 over 1. And what's the cotangent of 300? Adjacent over opposite, so it's going to be negative square root of 3 over 3. I heard a few people go, oh, that's good. That's a good thing. Talk to me, guys. You draw the angle, but you work with the reference angle. You draw the angle in blue, that's 300. That's the angle. But that angle created a reference angle here in red of 60. That's who you work with. Why? Why? Because that's the way it goes. We got to talk about reference angles. For any angle theta, written theta prime, or sometimes you could write it as alpha, okay, either or, is the positive angle made by the terminal side of an angle and the x-axis. Guys, I need you to really pay attention to this, okay? Because this is going to get real. Actually, you know what? Let's make it a little unmessy. Let's do this. Okay. Bear with me here, okay? Please, I'm going to go color coordinated. When I'm going to have 4 different angles here. I'm going to show you how you get the reference angle. When your terminal side ends right here in the first quadrant, the theta is your reference angle. It is your reference angle because the reference angle is formed between the x-axis and the terminal side. We'll call it TS. So that's my reference angle. Does everyone see that? Okay. Now, next one, guys. See, let's get orange here. Okay. So now I'm going to go this way. And this is my terminal side. This is my theta, right here. But who's my reference angle? This guy here in red. Why, Moro? Because the reference angle is always formed between the x-axis and the terminal side. Right? Let me erase it. Do another one. Let's do blue. My boy blue. Oh, wait. Let's do it the right way. Okay, so for blue, I went. Okay. This is my blue guy. This is my blue. That's my theta. Who's my reference angle, though? This guy right here. Why, Moto? Because it's the reference angle is made between the x-axis and the terminal side. With me? And then, last but not least, green. Bam. Green is my theta, but that's not my reference angle. My reference angle is right here. Why? Because the reference angle is formed between the x-axis and the terminal side. You guys with me here? So I always tell my boys or my students, remember a bow tie. The inside parts of the bow tie are my reference angles. Now, why do I have formulas here? Well, okay. If they're in the first quadrant, theta is the reference angle. That's it. If you're in the second quadrant, guys, to get my reference angle, it's just 180 minus the angle. So, for example, let's say that my angle was 120. I went, oh boy, sorry. I went 90 plus another 30, right? That's 120, correct?
Yeah.
What's 180 minus 120? Isn't that my reference angle?
I get it. If you go all the way over there, it's going to be...
Correct. If you go all the way over there, it's going to get to 180. Now here in this case, if I'm down here, it's your reference angle, which is greater than 180, minus 180. And then if you go all the way around, it's 360 minus your angle. But I never really even look at those. I just look at where's the terminal position, and then I just subtract from 90 because each one of these quadrants is 90 degrees. Is everyone with me on reference angles?
Yeah.
Okay. Okay. Find the reference angle for each. Check it out, my brothers. You'd go 90 plus 45 gives me my theta of 135, correct? But my reference angle, I'm going to make it in purple. My reference angle is this guy right here in purple, 45. Because 90 minus 45 is 45. And then from here, guess what, guys? This is 1, this is 1, this is square root of 2. Why, Moto? Remember the 45, 45, 90 triangle? And now I can find anything I want. Make sense? 120. Well, I went 90 and 30. So now this time I'll do it in blue. What's my reference angle? There it is, baby. There it is. Does that make sense? And now this will be 60, this will be 30, correct? So this is negative 1, this is square root of 3, and that's 2. Are you seeing that? Okay. Now, find the sine, the exact value. Find the sine of 240. No calculator. No. Oh, no. Check it out, guys. You don't need a calculator. 180 and 60. Isn't 60 in this case my reference angle? This is a 30, 60, 90, correct? So across the 30 is 1, but I'm on the left side, so that's a negative 1. Across the 60 is a square root of 3, but I'm under the x-axis, that's negative square root of 3. And my hypotenuse is 2. So what's the sine of this, guys? Sine of 30, opposite over hypotenuse. This is going to be, and I'm sorry, it's not sine of 30. Stupid, it's sine of 60. Opposite over hypotenuse, negative square root of 3 over 2. You don't need no calculator. Cosecant of 570. Whoa, cosecant of 570. Okay, don't stress it. Don't stress it. Look, 570. Well, first of all, can I find a coterminal angle here? Can I subtract 360? And am I not really just working with 210?
Okay, so moral.
Yes.
After the angle was above 360, you
Yeah, subtract or add 360 to get.
But you can't solve for 570.
Absolutely, you can't solve with 570, but then you're gonna go like this: one full 360, and then you gotta keep going. Why would you waste time or effort like that? You know it's a 210-degree angle. That's where it terminates. So I got 90, 180, and this time 30. 30. That's a 30, 60, 90. So guess what? Across the 30, negative 1, negative square root of 3, and 2. Now cosecant. Cosecant is the reciprocal of sine, right? So cosecant is hypotenuse over opposite, right? So the answer here is negative 2. Is it that bad? It's not that bad, right? Cotangent of 135. Well, I got 90 plus 45. So my reference angle is also 45. 45, 45, 90, I got a 1 negative, 1 positive, and a square root of 2. Cotangent is the reciprocal of tangent. So it's adjacent over opposite. So that's going to equal adjacent over opposite, negative 1. Cosine of negative 300. I'm going negative. So negative 90, negative 180, negative 180, negative 270, and then negative 300. This is 30, but what's my reference angle? That's right. My reference angle here is 60. You could have added 360 and just gone negative. You're right. I'm sorry. Should have done that. So then this across the 60 square root of 3, 2, and 1. So what's my cosine? Adjacent over hypotenuse. So that equals 1/2. That's power right there, guys. Talk to me, bro. Talk to me. Talk to me. Cake sauce? I love it. Okay. Suppose that theta is an angle in standard position whose terminal side is in quadrant 3, and the secant of theta is negative 4/3. Find the exact value of the trigonometric functions. Okay. Check it out. You ready? Because I'm going to destroy this. The quadrant, you're in quadrant 3, so you know you have a triangle here. This is going to be my reference angle, right? And I know that the secant from there, from my angle, is negative 4/3. So secant is hypotenuse over adjacent, correct? So this is 4. My adjacent is negative 3. Is that a 3, 4, 5 triangle? So now, what's the sign, guys? Opposite over hypotenuse, 4/5. What's the cosecant? Hypotenuse over opposite, 5/4. What's the cosine? Adjacent over hypotenuse, which is negative 3/5. The secant they already gave you. Wait. Whoa. I did this wrong. Hold on. The secant is the reciprocal of the cosine, Moro. So that's hypotenuse over adjacent. Sorry. Hypotenuse. Look. This is my hypotenuse. Sorry, guys. I messed up. That's my hypotenuse. That's my adjacent. So to find this guy, it'd be. Come again? Yeah, but you can't have a negative here. The negative will come from this side or from the y side. So 16 minus 9 is 7. So this is the square root of 7. Now from here, you can find all the trig functions that you have. You with me? The last one real quick. Okay. So the robot competition, robot's arms 4 meters long, is to pick up an object point A and release it in a container at point B. The robot's owner programs the arm to rotate through an angle precisely 135 to accomplish this task. What is the new position of the object relative to the pivot point? Okay, so I'm going up 90 and then 45, right? So right here, this is my 135. This is my 45. So this is negative 1. This is 1. This is square root of 2. So what's the point on this circle here? Negative 1, comma 1. That's the position. Because if I saw this, what's really happening is this. This angle, like I said, traveled, and it ended right here. and that's my location. Amazing class, guys. Thank you so much. God bless you. I hope you learned a lot and have a wonderful day. Bye-bye, guys.